Now we are going to study the experimental setup to study photoelectric effect. Okay, this experimental setup was designed by Leonard and Millikan. So this is the setup. Here is the photosensitive plate and here we have got receiving plate. Light of appropriate frequency falls on this photosensitive plate. So let us say blue light is falling on this photosensitive plate. So what will happen? Electrons will come out because of photoelectric effect. So these are the electrons that come out of the photosensitive plate due to photoelectric effect. Now, if this receiving plate is kept at positive potential, as is the situation now, the electrons will easily reach the receiving plate and current will be seen in the galvanometer. Even if we keep the receiving plate at zero potential, some high energy electrons will reach the receiving plate and current will not be zero. Now, suppose we make the potential of the receiving plate more and more negative. So we can adjust the potential of this battery with the help of a rheostat. So we make the potential of the receiving plate more and more negative. At some negative potential, even the most energetic photoelectrons will not reach the receiving plate and current will become zero. The negative potential at which the current just becomes zero is called stopping potential. This stopping potential is a measure of the maximum kinetic energy of the photoelectrons. K max will be given by the charge of electron multiplied by stopping potential. So by measuring the stopping potential, we are getting an idea of the K max of photoelectrons. Now, suppose we do the exactly opposite thing. We keep the receiving plate at positive potential and we keep on increasing the positive potential. So this is the situation now. We are increasing the positive potential. As we increase the positive potential, more and more photoelectrons will reach the receiving plate and current will keep on increasing. At some positive potential, all the photoelectrons that are coming out will reach the receiving plate and current will reach maximum value. This maximum value of current is called saturation current. Saturation current is a measure of the number of photoelectrons. This is the most important thing that you need to learn in photoelectric effect. There are two things. One is stopping potential. Stopping potential, when you apply, even the most energetic photoelectrons are stopped. So this is a measure of K max of photoelectrons. Saturation current is the maximum current you can get in a particular setup. So that saturation current is a measure of number of photoelectrons. Now, this stopping potential depends on the frequency of light and saturation current depends on the intensity of light. Now, there are two important graphs that we can make from this experiment. In both the graphs, photocurrent is on the y-axis and the voltage is on the x-axis. So this is voltage, this is photocurrent. This is voltage, this is photocurrent. Now look at the first graph. In this graph, the intensity of light is kept constant. What is intensity? Remember that? It is energy per unit area per unit time. So you are keeping the intensity constant. We are changing the frequency of light. Now, for one frequency we get this graph, other frequency we get this graph. there is some stopping potential at which the current is 0. As you increase the potential from there, current keeps on increasing till it reaches a maximum value, and that is saturation current. So, this is stopping potential, this is saturation current. Saturation current is a measure of number of photoelectrons, and stopping potential is a measure of Kmax of photoelectrons. Now, when we change the frequency of light, keeping intensity constant, saturation current, which is a measure of number of photoelectrons, does not change, but the stopping potential, which is a measure of Kmax of photoelectrons, changes. This is very important to understand that when we change frequency of light, the stopping potential changes, Kmax of photoelectrons changes, but the saturation current does not change. So, stopping potential, which is a measure of Kmax of photoelectrons, that depends on the frequency of light, right? So, stopping potential, which is a measure of Kmax of photoelectrons, depends on frequency of light. Very important. Now, here what is happening? We are changing the intensity of light. Earlier, say, intensity I of light was coming. Now, you double the intensity, keeping the frequency constant. Frequency constant means color of light is same. So, blue light is falling. Now, double the blue light is coming. More energy per unit area, per unit time is coming onto the plate. Now, we find that the saturation current changes, but the stopping potential does not change. Saturation current, which is a measure of the number of photoelectrons, this depends on intensity of light, not on frequency of light. These were very important observations. Based on this, the particle theory of light came, right? Einstein used these results to give the particle theory of light, which we are going to discuss in detail. Stopping potential, which is a measure of Kmax of photoelectrons, depends on frequency of light. Saturation current, which is a measure of number of photoelectrons, depends on intensity of light. Please remember this very, very clearly. These two things must be ingrained in your mind in separate places, right? Keep this on the left side of your head, that on the right side of your head. Stopping potential, measure of Kmax, depends on frequency of light. Saturation current, which is a measure of number of photoelectrons, depends on intensity of light. Now we will try to understand why these observations cannot be explained by wave theory of light. The observations are stopping potential, which is a measure of Kmax of photoelectrons, depends on frequency of light, not intensity. And saturation current, which is a measure of number of photoelectrons, depends on intensity of light. Now, let us try to see this point. Here is a metal surface. Same metal surface is here. This surface is, say, photosensitive for blue light. Okay, I have got blue colored pen, so this is photosensitive for blue light, and say, let us say, it is not photosensitive for green light. If some surface is photosensitive for blue light, it will be photosensitive for all light that is having more frequency than blue. That means it is photosensitive for blue. Then it is photosensitive for indigo, violet, ultraviolet, X-rays, gamma rays. all it will be photosensitive. If it is not photosensitive for green light, then it will not be photosensitive for yellow light, orange light, red light, infrared light. Then after infrared, microwave, radio waves. All this it will not be photosensitive. It will be photosensitive to everything that is here, this side, not photosensitive to anything that side. If something is photosensitive for blue light, it will be photosensitive for any color of light having higher frequency than blue. It is not photosensitive for green light, it will not be photosensitive for any color of light having lower frequency than green. So remember that. Now this surface is photosensitive for blue light. That means this metal, whatever is there, is photosensitive for blue light. If blue light falls on this, electrons come out. Suppose a small amount of blue light, low intensity blue light falls on this surface. Electrons will come out. They will come out with some Kmax. Suppose we put a high intensity blue light. All the blue light in the universe suppose falls on this metal surface. Then more electrons come out. But the Kmax is same. Whether a small amount of blue light falls on the metal surface, a low intensity blue light falls on the metal surface, or a high intensity blue light falls on the metal surface, Kmax is same. According to wave theory, this much blue light has got much more higher energy and more energy is falling on the metal per surface per second. So electrons should come out with more Kmax. But actually they come out with the same maximum kinetic energy. So this is the first problem. According to wave theory, Kmax of photoelectrons should depend on intensity of light. But actually they do not depend on intensity of light, they depend on frequency of light. So this the wave theory could not explain. Low intensity blue light, high intensity blue light, the Kmax is same. Now let us look at the second problem. This is same surface, same metal, same surface. A very low intensity blue light is falling on this surface. Right? Electrons happily come out. Green light, a high intensity green light is falling on the same metal surface. Maybe all the green light in the universe now falls on this metal surface. No electron comes out. Now as per wave theory, this much green light will have much more energy than this much blue light. Right? This is very high intensity, this is very low intensity. Here more energy is falling per second. So here the electron should come out easily. But actually it does not come out. So the second problem is, according to wave theory, photoelectric effect should occur for any frequency of light. If the intensity is large enough, but actually photoelectric effect does not occur if frequency is less than threshold frequency. A very low intensity blue light is sufficient to make the electrons come out. A very high intensity, a very high intensity green light is not able to make any electron come out. So this again cannot be explained by photoelectric effect. Now let us look at the third problem. This is that same metal surface. Blue light is falling. Okay. How much blue light can actually hit one electron? Even if the electron is able to absorb energy from nearby areas, how much actually it can absorb? Electron is very small. So it should take time to absorb the required energy, then only it can come out. It cannot come out immediately. because electron is very, very small. So therefore, the electron should take time to acquire the required energy and then come out. In fact, you calculate the time, it comes out to be hours. So this electron should take time to absorb the required energy and then it comes out. But actually, it comes out immediately. This absence of time lag cannot be explained by wave theory of light. So there are three things which the wave theory could not explain. First thing, according to wave theory, Kmax of photoelectrons should depend on intensity of light. But actually, Kmax of photoelectrons does not depend on intensity of light, it depends on frequency of light. Second point, according to wave theory, photoelectric effect should occur for any frequency of light if the intensity is large enough. But actually, photoelectric effect does not occur if intensity is less than threshold frequency. Third problem, electron is very, very small. So how much light can it absorb at one time? Very, very little. Even though a lot of light is falling on this metal surface, a very small amount of light only from nearby areas the electron can absorb. Therefore, the electron should take time to come out of the metal surface. But actually there is no time lag. The electron comes out immediately. So these were the three problems that the wave theory of light could not explain. And Einstein had to come out with his particle theory of light to explain this.